All right, let's talk about gradients and let's talk about gas exchange. Partial pressure is a little bit different than concentration. Okay, you can't just call it a concentration gradient because there is also a pressure gradient. So if you have two containers of gas separated by a membrane and one side is under more pressure than another, the effective concentrations of gases are at a higher pressure in the pressurized one, so they're more concentrated. They are pushed into tighter space because of that pressure. So it's as if their percentage was higher. This is not something you can do with water because water cannot be pressurized. I mean, you can put it under pressure, but it doesn't pack down any. Okay, so you can't cram more water into the same space, but you can with air. So if you have twice as much air in one container versus another, it's even though it still may only be 20% oxygen, it's got twice the oxygen aggressiveness to it. It's like it's 40% oxygen if you were trying to let it flow back and forth between two containers because all of its oxygen's trying to, it may only be 20%, but this other side that might be only 20% has half as many actual oxygen molecules in it. It's like, think about it this way. What if you had a near vacuum on one side and 1% of the vacuum was oxygen versus a regular atmosphere on the other side that only had like 1% oxygen? Obviously, the regular atmosphere is, no matter what the gas is, it's going to force its way into the other side because of the lack of pressure. Get it? Okay, so there we go. That having been said, it won't have a big impact with the way we treat it, but later on when you take some physiology classes, air pressure has a lot to do with your ability to breathe. Okay, so when the air gets thin, that's why it becomes hard to breathe because the air is not pushing its way into the oxygen is not trying to push its way into your capillaries in the lungs because there's not enough actual air pressure to get it going. It's like there's rarefied air. You don't get as much oxygen. Okay, so then anything you're going to respire through has to be wet. Dry things don't do good gas exchange. So when you're doing this, you're going to have a wet surface. If you're a fish, congratulations, all of you is wet. If you're an amphibian, that's why you have to keep your skin wet. And if you're one of us vertebrates, you're going to definitely have to, or when I said vertebrates, excuse me. I've been using that term vertebrate way too loosely. I apologize. I just realized I've been using the word vertebrate to mean tetrapod this entire lecture. Because I was talking about vertebrates as having, the double circulation, but fish, some of them have single circulation, and fish are vertebrates. So I apologize to my friends, the lower vertebrates. Oh, there, I just insulted them again. Okay, coming back to it. Fish don't have a problem keeping their gills wet. Amphibians have to stay near the water, usually because they have to keep their skin wet. But the reptiles and the mammals, we can walk away from the water because our respiratory media is inside our body, and we can keep that wet easier. By the way, no longer is it called respiration. It's called ventilation, even though I know the chapter's on respiration, and circulation, right? No, ventilation, that's when you're moving air in and out, okay? Because respiration, as far as biologist is concerned, is something that happens inside of a cell. All right, so there you go. There's your let me screw with your brain for a little bit on that. That having been said, when you get to medical school, you'll switch back to calling it the respiratory rate instead of the ventilatory rate. But life's full of problems. Most important thing I want to tell you about fish is that fish are way cooler than we mammals. Yes, there it is. I said it. They make use of countercurrent exchange. Countercurrent exchange is one of my very favorite ever things, and we've already talked about it in the legs of geese and how they maintain their heat. And remember that it's the concept of having the blood flow go in opposite direction of the concentration of whatever you're trying to change. So in the geese, it was you have your blood flowing down into colder water while you have cold blood flowing back up past it, stealing its heat before the water can steal the heat. In this case, what you're going to have is deoxygenated blood flowing in opposite direction from oxygenated water. Birds who have weird air sacs in their body and they'll breathe, each breath of air kind of cycles through their body. Each time they inhale, the air gets pushed further around a circuit. They also use some countercurrent exchange. Those birds do, but we're not going to talk about it specifically. But it's just the idea that in the first lung, that's the most highly oxygenated blood is touching the most highly oxygenated air. In the last lungs of the circuit, that's the poorest oxygenated blood touching the poorest oxygenated air. So you're still going to get oxygen transfer, and that poorly oxygenated blood that is now like 1% higher in oxygen is the blood that's headed towards that highly oxygenated lung so that it's picking up oxygen at every stage. Now, that was a little bit hard to conceptualize because you didn't have a picture. Let's do it in fish. As water flows across the gills, okay, the blood is flowing this direction. So the water, as it comes in, is highly oxygenated. Okay, it's hitting blood that's almost as highly oxygenated as it. So the blood's going to steal a little bit of oxygen. Okay, and then as it moves forward, now you're like, oh, well, it's not as oxygenated. Wouldn't the blood be at equilibrium? No, because the blood it's encountering is even lower in oxygen than the blood before. So as you start, you have low water oxygen, but still more than the blood, and so you pick up a little, pick up a little, pick up a little, pick up a little, pick up a little. So you can get 140 compared to 150. Okay, so you can get very close to the oxygen content of water, which is very convenient since water doesn't have an extremely high oxygen content. You want to take as much as you can. You can be a little bit sloppier with the air you breathe because air is 20% oxygen. It's a lot higher percentage. If you didn't have this, the best that you could get is around an 80-80 mix. 75-75. If blood was flowing in the same direction as the water, once the water had dumped off half of its oxygen to the blood, they would be at equilibrium. And so you couldn't take any more. There's no way to supercharge your blood with oxygen. Okay, that's countercurrent flow for you. Pay attention. Countercurrent flow showed up in heat. It's showing up in water, and it's going to show up in oxygen. It's going to show up again when we do the kidney. So pay attention to this countercurrent flow. Blah blah lungs. Study the lung anatomy on your own. I'm not going to talk about that. Except note when you cough to clear your throat and you're clearing out a loogie, you can go ahead and swallow it right away. It's not going back down to the same place. I know your mom told you whenever you were sick, don't swallow it back down because then it's going right back down to your lungs. Are you kidding me? You don't swallow into your lungs. You swallow into your stomach. So the lungs are designed to constantly be moving mucus and any trapped bacteria or particles in it up into the mouth, and either you spit it out or you swallow it down into a boiling pit of acid, which is your stomach. Either way, the bacterium are dead. And if you're a smoker, you really need to quit right now because your mucus escalator is breaking down. The smoke is killing off the cilia that wave upward, moving that mucus up, so that's why you get that cough. You have to use muscular contractions to shake the mucus and to squeeze it upward, okay, break it free, that kind of stuff. And so what's happening is mucus is puddling down in your lungs, and the bacteria that it's trapping is supposed to be moving up is instead having a party and giving you respiratory infections. All right, breathing. Let's talk about negative pressure and positive pressure. Okay, you breathe by negative pressure. You have a vacuum. As your diaphragm contracts, okay, it pulls downward. Okay, that increases the volume of your lungs, and that's going to suck the air inward like a balloon. Similarly, your rib cage, which has muscles on it, pulls outward. That's why your chest is supposed to expand a little bit when you breathe, and if somebody's pushing down in your chest, it's kind of hard to breathe. Okay. Further, that's why if you break if you break a rib, breathing hurts like a some gun because you're flexing that rib and muscles are pulling on it the whole time every time you breathe. This is negative pressure. Positive pressure is the reverse. Frogs, have you ever noticed that they seem to be swallowing constantly? Instead of sucking air in through a diaphragm, they swallow air. They take a mouthful and press it downward as if it was food, shoving it with muscular contractions, closing and pushing forward. Okay, that's positive pressure. That's not how you breathe. It's also not as efficient because you have to push it all the way down. You have to have multiple push points. But for you, with negative pressure volume, you have a much greater tidal volume. Okay, one muscle and a few around the ribs can move and you suck in a gigantic volume of air. Okay. Here's another weird thing. You don't control your breathing rate based on the amount of oxygen in your blood. Did you know that? That doesn't make sense. Oxygen is the most important part. Well, yes, it's true, but oxygen sensors are difficult to make and extremely unreliable. Instead, you control it by carbon dioxide sensation. And you don't even really do that. You control it by pH sensation. See, carbon dioxide changes the pH of a fluid, right? And so, a carbon dioxide or oxygen sensor would be great, but they're difficult to make. However, a pH sensor is really easy. You just have a protein that denatures at certain pHs, and as it denatures, it starts to give you a signal. Shape change in proteins based on pH is one of the easiest things to do in the world. So a part of your brain called the medulla looks at the fluid. Okay, not even the blood. We're talking about the interstitial fluid. In this case, it's called cerebrospinal fluid because it's around the cerebrum, the brain, and the spine. But just this interstitial fluid, if the pH goes too acidic, that means there's too much carbon dioxide, which means you're going to breathe more. Okay, and then that's how you pretty much regulate whether or not you need to breathe. Okay, Now you do have some backup O2 and CO2 sensors, but they are less reliable, so they're secondary control. They're more emergency control, just in case something weird has gone with your blood, like if your blood starts becoming extra acidic for other reasons, like you're in ketoacidosis or something weird like that. Then you need a backup sensor to really tell you what's going on, or else your breathing rate will go haywire. Okay. Now, let's talk about how gas exchange works. All right, hemoglobin. Just get down to the hemoglobin. Okay, hemoglobin cooperatively loads and cooperatively unloads. Okay, remember induced fit? Back when we were talking about enzymes that bind to things, they'll bind to their substrate, and when they do, it will actually pull the enzyme to click in place around the substrate and change the enzyme's shape a little bit. Well, hemoglobin forms a homotetramer. It tetramerizes. It puts 4 hemoglobins in a circle, okay, and they all touch each other. And as one of them grabs hold of oxygen, it causes a slight shape change, which induces the fit to the oxygen and resonates throughout the molecule, causing the other hemoglobin molecules to try to grab onto oxygen as well. It's like a jealousy thing. Okay, so it pushes this cascade. It alters the equilibrium slightly. Once one of them grabs hold, the equilibrium drives further towards binding oxygen. The reverse is also true. When one of them lets go of an oxygen, it uninduced fits, so it flexes backwards. That pushes on the other hemoglobins to dump their oxygens as well. So it shifts the equilibrium back the other way. Why do you do this? Well, the reason you do this is evolution has accidentally come up with a really nifty trick that you can rapidly load oxygen onto hemoglobin. It will suck it up in one set of conditions. Where oxygen is high, it will suck up as much as it can because the protein actually changes shape to be more receptive to oxygen. Then when it moves into an area when oxygen is low, remember how equilibria work. The oxygen's always jumping on and off. It's trying to jump on and off. The moment it jumps off, we have pushed the equilibrium to the other side of the equation where it is less favored towards oxygen. And now it dumps off all of its oxygen very rapidly, further than it would if it was a static protein. So it can pick up more and dump off faster than if you kept it static. Because if you kept it static and made it to where it would pick up oxygen more, then it wouldn't drop off the oxygen when it got to the veins or to the capillaries. It would want to hold on to it if it were a static protein. Or if you made it to where it was happy to dump its oxygen, it wouldn't grab as much to begin with. But when you make it to where it's like this dual personality protein where it will grab the oxygen really hard when it's got lots and dump it off like a bad habit when there's very little to be found, okay, there you go. It's totally a two-faced friend. It's the friend that thinks you're great when everybody else thinks you're great and totally abandons you whenever something goes wrong. That's hemoglobin. Okay, it's brilliant. Similar scenario. Bohr shift. Okay, pH changes we know change proteins. Well, when the pH goes acidic, hypothetically from extra carbon dioxide, then what you get is you get an increase of dissociative scenario. So what happens is the hemoglobin in the saturated tissues picks up less oxygen and also offloads it faster. Okay, now this can be a bad thing if you have acidic blood because you're not as efficient. Or it can be a great thing if over here in the lungs you didn't have acid. But over here in the tissues that are exercising, okay, what we've got is we've got an offloading going on. Actually, I've been indicating this completely backwards. Gosh, I wish I cared enough to go back and re-edit this. Let me indicate that the other way. Okay, here's your lungs picking up as much oxygen as possible. Here's at normal pH. Here's at it's still neutral to basic, but it's more acidic than it should be. Okay, so what happens is if this were your lungs that were acidic, they wouldn't pick up as much oxygen. But let's say your lungs are normal and they've picked up plenty of oxygen, but they get over here into highly exercised tissues which both have less oxygen. Okay, we'll dump off some oxygen, and bonus, are also acidic because they've got extra carbon dioxide. Dink! We just got a bonus kick of 10% oxygen offload. So that may have been confusing, so let me say it one more time. The Bohr shift is a bad thing if your whole bloodstream is acidic or less basic than it should be. But it's a good thing if you've got a tissue that is specifically high in carbon dioxide because it's working out really hard. That tissue is going to be fed an extra dose of oxygen because the Bohr shift causes hemoglobin to just let go of the oxygen faster. You get it? This is another thing that happens with animals that can hold their breath for a long time. As the blood circulates through the body, it's not picking up any new oxygen necessarily, but as the tissues get anoxic, they start getting extra carbon dioxide to boost out. The pH drops, and a little bit of extra oxygen kicks out of the bloodstream at the 10 or 20 minute mark to keep the thing going as it's, diving for long periods of time. Now, hemoglobin is not just good at transporting oxygen. Hemoglobin is also great for transporting carbon dioxide, and here's how. It cheats. Okay? What you do is, and this is also the red blood cell that does this, it has some enzymatic components. The carbon dioxide gets converted into carbonic acid in water. Okay, that's just natural. You pump carbon dioxide into water, it turns into an acid. We've already discussed that. By equilibrium, it also can convert back into carbon dioxide. So what do? Well, you steal a piece of the equilibrium. Hemoglobin can not only bind carbon dioxide, it's also very good at picking up hydrogen ions. So it deacidifies the blood just a little bit, but in the process locks that bicarbonate in place. Now it can't go backwards because it's missing its hydrogen ion. And further, we're driving that equilibrium forward, okay, because we've pulled out one of the two products, and an equilibrium is always based on the two products, not just the one. So we've reduced one product, so that drives our equilibrium forward even more. So the more CO2 comes in, loads up on the hemoglobin. We also, some of that CO2 turns into bicarbonate. We trap it as bicarbonate, with this H plus here. Now that drives even more CO2 to want to go forward, because there's less CO2, quote, in the blood at this point. Okay, and there's less of these products as well, so it wants to make more carbonic acid. You get this process? So we're cheating. We're locking up CO2, but we're also locking up hydrogen ions to trap CO2 as bicarbonate, so that more CO2 will be pulled out of the tissues and into the bloodstream. Then when you get to the lungs, once again, hemoglobin is a tricky thing. It reverses its preferences and suddenly starts dumping its hydrogen ions and dumping the carbon dioxide. So suddenly the blood levels right at the lung go way up in carbon dioxide levels. And it's that cooperativity again. Once one hemoglobin, one pair of the tetramer unloads, all of them start to unload. So it's an either or process. And that is the end of this lecture.